Hi guys. Thank you. Wow, I didn't even do anything yet. Hi everyone. Thanks for coming. Yeah, it was a great session last hour, and I hope I can follow that up well. Yes, I will not be taking a break, but I will do my absolute best to keep you fully enthralled. But you do have a break right after this session, so you'll actually get to get your coffee and everything. So sorry about that, but I think you'll appreciate it. I hope. Yes, I'm wearing, this is what I look like without a beard. And obviously, I guess I was wearing the same shirt, which is also unfortunate. But I'm from the University of Oklahoma in the United States. I am here working in Germany for a while, and happy to be here with you today. I actually got my master's near my hometown in Oklahoma, which is one of those flyover states. And I worked in oil and gas for about 7 years right out of college. I then moved to the East Coast in the United States, where I began working with Cloudera. I worked with them for about 2 years, and then I began Databricks about 2.5 years ago, and have been enjoying it ever since and learning more than I can imagine every day. So what are we going to talk about in this extremely long session? Well, I noticed that every time I go to a client, I work a lot trying to help them optimize their workloads. But a lot of times we talk past each other for a bit because there's a little bit of baseline. There's actually a lot of baseline that I think that they understand, but they don't. So I'm going to use a little bit at the beginning to cover some stuff you probably know, but only a little bit of this time will be stuff that you probably know. And then I guarantee you that we'll find something that you don't know, okay? I'll find something. So please bear with me in the beginning. If you know it, please pay attention because there will be little nuggets that we'll build on later. I'm also going to talk about the UI. We're going to go into a demo session here with the Spark UI, and I'm going to walk you through the different components of that UI so that we can build more of a foundation on top of that. Then we're going to go into the actual goodies of how to right-size your job and optimize it, and then go into advanced optimizations in the second half of this talk. Okay, and I know this isn't what you wanted to see because you know what a driver and you know what an executor is. This is an advanced talk after all. However, let's just take a moment and baseline because I think there are some misconceptions here. Yes, we do have a driver and we have one or more executors. Each executor, these are still servers, right? So they have cores and they have a certain number of cores. Let's just say they have 8 cores. A core is also ubiquitous and synonymous with a slot. So we can use a slot to put workloads into. So each core can take one slot or one piece of memory, one piece of work. Each server also has memory, but not all of it is given to Spark. By default, about 90% of the server's memory is given to Spark. But that server memory is further broken down inside of Spark across storage memory and working memory. Storage memory is where we cache and persist things. Working memory is where we actually use to do our work in Spark in our in-memory computations. Now, when we first start doing our workloads, we have all of that Spark memory available to do work with. But up to a certain percentage, we start to consume that when we cache and persist things into memory and give ourselves less space to work with as we get further, as we use more and more of it for persistence. So that might mean that we're going to get spills earlier. That default split is 50%. So by default, you're allowed to persist stuff in memory up to half of the memory that's available to Spark. Now, what a lot of people don't know is that each server actually has locally attached storage as well. Well, hopefully it's locally attached. It's mounted as if it were locally attached anyway. So these could be RAM disks, these can be SSDs, but they can also be hard drive disks, HDDs, or unfortunately they can be remote NFS drives, which are extremely slow. These disks are extremely important because a lot of times in Spark we do things called shuffles, right? We move data around. And in the intermediate stages, when that data is moving around, that data goes to disk. And we hope that that disk is extremely fast. The faster the disk, the faster the shuffle. Shuffles are still slow, but they're faster if the disks are faster. So it is important that we have fast disks. So now we talked about the hardware hierarchy. Let's talk about the software hierarchy a little bit. So actions are the only eager thing that we have. As soon as we call an action, work begins. Up until we call an action, we're basically just staging work through transformations. There are 2 types of transformations, narrow and wide. A narrow transformation is a change in the data or a maneuver of the data where all the data is contextually available to the same CPU at the same time. So that's a narrow transformation. A wide transformation is something like a join or a group by that requires us to move data around. And a lot of times I think of these narrow and wides versus like what's in a row versus what's in multiple rows or multiple tables. If it's inside the row, generally it's within the context of a narrow transformation, therefore it's efficient and quick. Now, when we call an action, we spin off all those transformations that we've set up. We've called all of our selects, our casts, our joins, our group bys, all that's been told to Spark what to do. We call the action to go or to do the write, and we begin our job. That launches one or many Spark jobs, depending on what we're doing. Those Spark jobs are full of stages. Those stages are then the actual work that's going to be done. So jobs can have many stages, meaning that each stage is a section of work that's going to be done, and a task is inside of a stage. So we can have many tasks inside of a stage, and each one of those tasks do the exact same thing, only on a different part of the data. So each task is the same, but on a different piece of data, so the same computation. Now here's where things start to get interesting for people that are trying to optimize Spark correctly. A task is operated on by one slot, one processor. And that also operates on one partition of your data, one Spark partition of your data. So one task takes up one core at a time and takes up one slot. All of those things kind of mean the same thing. Also, tasks are the only thing that interact directly with your hardware. Everything else is meant for kind of organization and structuring of the process. Okay. So I want to take you through the UI real quick. Let's see if the demo gods like me today. So I've got a little bit of work here. I'm just going to go ahead and kick this off. And I'm going to show you how the Spark UI, oh boy, I knew that was going to happen. Let's see. How do I switch this? I'm going to do it this way. 1 second. Oops. There we go. All right. So I've kicked off this little job that's going to do some work, which we'll talk more about in a little bit. But if I go over to my Spark UI here, you'll notice that the organization of a Spark UI is very, very similar to that organization of that software organization I just talked about. Jobs full of stages, full of tasks. So if we look at the Jobs tab right here, you can see I have something running. It's running 97 tasks right now. I don't know why it should be running 96 because I have 96 executor cores, but I got a free one. Cool. Now if you click on this description here, the way that it's structured is I click on the description of the job, which will take me into that stage. When I go into that stage, so now you can see I have one active stage running inside of this job, and it's executing currently, and I can see inside of here exactly how many I have. So I have 452 partitions of data being operated on at the same time, well, to be operated on, 96 of which can be operated on at the same time. Now here's where it actually gets interesting. When I click on the description of the stage, I can go and look at the task detail for that stage. Here you can see at the top the stage details, the cumulative stage statistics. Here I see that this has been running for 1 compute hour so far. That's the wall time times the number of cores. And then I have my input size for this stage, which is 10.7 gigabytes so far. And I've written out to shuffle write. Now, where's that write going? Local disks, right? That shuffle write right now is writing out to disk because the next stage is going to then read from those local disks. Again, why those disks are so important, to be fast. Here is potentially the most important part of the entire Spark UI. Well, I won't get into that argument, but this is very important. So here are the quartiles of how my data is arranged across my partitions. This is across my quartiles of partitions. This is really important to be balanced. We want to have good balance here. This is how you can detect skew, and we'll talk more about that in a minute. But what I like to do is I like to control or command click on this in the UI to get a full screen page of this. And now you can see what's going on. I have a shuffle stage going right now. If I click on this, and as I refresh this live, I'm getting new data. As things complete, I'm starting to see them in real time. The next item, we'll go into this more in detail as we get further. I just want to give a baseline for those of you that may not be as advanced in Spark. The storage tab is where we see our persisted data, anything that's DBIO cached or whatever. You'll see that here. So persisted stuff is going to show up here. I'm going to skip this environment tab, but if you want to see what your environment configurations are, you can go there. The executors, I use this tab occasionally, but I really use it whenever I think there might be a node level issue. Maybe like it happens sometimes where in Azure or AWS I wind up with a node that's kind of flaking out, and I can identify that really quickly if I see one node starting to fail all tasks. It's either my fault or it's actually a bad node, and it's going to require a little bit more digging to figure that out. But this gives me actual server level statistics. How many of you use this SQL tab every day? Show of hands in your workloads. Great, great. Because this is actually how we optimize workloads, how I find out what's going on. And in a typical workload, this is what I do. So this is my job, to figure out what this does. And now this looks really intimidating, right? And it is. But it's really easy, and we'll go into this a little bit more in a minute, but it's really easy to dig through this if you just kind of zoom out and look at the big picture. You start to look at the lines, where are the commonalities in this craziness, and so forth. So we'll go back to this in a minute. Now I'm going to play with the screens here again. Let's see if I can make this work again. Sorry about this. It's so fancy up here, I'm not used to it. Oh, I did it. All right. So now that you have a basic understanding of the structures, I mean, you probably already did, but I just wanted to make sure everybody was on the same page. We're going to go into the actual hardware. Now, we are still operating, and a lot of people forget this when you're in the cloud, but we are actually still on servers, so it's important to understand that servers are not ubiquitous. They still have cores, they still have speeds and memory speeds. You know, all those things, if you've nerded out and built your own computer, all those things still matter, so make sure you understand them. How many cores does a server have, and what is the speed of each core? What's the boost clock of those, and what is the average base clock? Knowing that, especially as you're moving into machine learning, is extremely important. So keep an eye on that. Also, it's super important to understand how much memory per core, not the memory that you have total on the server, because that just doesn't really tell you anything, because realize each core of that server is working on a subset of the data at one time and requiring a piece of memory. So what is that ratio of memory to core? That's what's actually important, so know that. And then the local disk I told you is already extremely important. Not only how big the disk is, because in the cloud, the bigger the disk, typically the more IOPS you get, right? The faster, the better the speed. Also the type, is it SSD or is it actual spinning disk? And then a lot of times you can have more than one disk. So that'll actually parallelize your throughput even more for those shuffles and those anything that's coming back and forth to disk. If you're pulling a lot of data over the network, reading a lot of data from the cloud provider, or shuffling a lot of data, these network speeds actually become important. So it might be much more efficient to have a few extremely large servers with 25 gigabit NICs rather than having a whole bunch of 1 gigabit NICs and moving a lot more data. Because if you think about it, if I can get server locality, I'm going to save the network. And when I do have to go to the network, if it's 25 times faster over the network, fantastic, right? So keep an eye on that and understand your workloads and make sure you get the right server for the workload. If you're efficiently using the server, it should cost you the same amount of money or less to do the same workload no matter how many cores you have and how the structure of the servers are. Okay, the next thing that most people forget is that these cloud storage data leaks, they aren't infinitely fast. You can break them. You can denial of service them, especially with Spark. And it happens all the time. People get 2,000 servers, 2,000 cores, and they try to write data down to Azure Data Lake or S3 with 2,000 cores at one time, and they're like, it's not any faster. Well, you're denial of servicing yourself, so you would actually go just as fast with 600 cores. So we'll talk about how to get around that and how to trick the cloud provider and let you go faster in a few minutes. And then also know how much your workload costs. Like, be respectful and conscientious of what you're doing. Just like as if it were your money, if you think about how much money your cluster costs, maybe you can scale down your data and save some money for yourself and for your client, or for your customer, or for your employer. So the first thing that I do when I go into optimizing a workload is to get a baseline on what the problem is. Like how good or how efficient or inefficient is this job to begin with. So I start in the Spark UI, and I look at stages that are running the longest. I didn't show you, I forgot, but you can actually click on the top title bars there in any of those sections and sort primarily by duration as a good example. So if you want to get the biggest bang for your buck when you first start doing an optimization, just do a descending sort on duration and find the stage that's taking the longest amount of time and dig into there. Also, you can look for spills. We'll talk a lot about spills here in a few minutes, but that is extremely important, looking for and identifying, sorting by the biggest spill count. The biggest spill, that'll really speed it up if you can get rid of that. Oftentimes, that's the same as the longest task, or the longest stage. The next one is CPU utilization. We want to see stuff like this, right? We want to melt the servers in the data center. If we're paying for them, we might as well melt them, right? So what we want to do is get that as high as we can. Now 125% is a little bit much for a production workload, probably. I typically like to see us average around 70 or above. So if you're looking for what is a proper utilization target for your production workloads, it's 70%. In fact, a lot of my clients, I instruct them and guide them towards, if you're not getting 70%, you should be doing code reviews and getting exception processes in place to allow production workloads that aren't hitting 70. And maybe depending on your organization or your area, that's not the right number, but define a right number for you. 70% is typically a good number, and you can get higher or maybe a little lower than that, but that's usually a good idea. Okay, also, I got this graph. If you don't know, there's a metrics tab in the Spark UI or in Databricks, and if you're not using Databricks, you can actually maybe you have ganglia reports or something like that. That's what this is from, is a ganglia report, and that's a really good way to see how everything's working as far as utilization graphs on network, memory, CPU, etc. Okay, so let's talk about the easy stuff. I promise you I'm only going to spend a few minutes here just to cover this base. But this is probably the most important thing to do, is use lazy loading, right? You have to minimize the amount of data that we're scanning. The easiest way to do that is lazy load the data. Use data skipping. So in Hive, most of you have come from probably a big data background where you know how to do this. And these Hive partitioning, making sure that you as a data engineer, if that's what your role is, making sure that you're making it easy for the consumers of your data to understand and identify these Hive partitions, these columns that are actually Hive partition, is absolutely critical. If you're not making it clear and obvious, maybe you put a P underscore and make that a rule and send out communications. Make sure your BI analysts know this. If you are a BI analyst or a data consumer and you don't know what I'm talking about, you're going to need to go do some reading, like today, because you really need to understand how to use these. If you do not, this is an advanced session, so I'm not going to bore you with Hive partitions today, but please do go research it if you don't know what I'm talking about. If you're doing bucketing, you're probably doing it wrong. So if you don't know if you're doing it wrong, turn it off and see if your job goes faster. If it does, you did it wrong, and you shouldn't be using it anyway. Bucketing, I'm not going to go into details about today because it's extremely hard to maintain, and that's probably even a deeper session than what we have time for today. But it's really bucketing, I think, is a good use case for purpose-built workloads where you know how to arrange that data properly for that purpose-driven workload. Trying to build a data lake or bucket on some kind of production workload where the data is consistently changing and you're adding new data every day, absolutely impossible, in my opinion, to manage that and keep the compactions correct and keep the sizing right without Delta. I've tried it several times, and if you know, please reach out to me after and teach me because I've struggled with this for a long time. I'm not going to advertise Databricks Delta or anything like that. I think everybody else has done a good enough job probably of that. But if you are on Databricks, or if you're using the Delta Lake, it's really important that you understand what Z-ordering is because it is a very efficient way of further lazy loading. So if you don't know what it is or you don't know how to use it, if you're on Databricks or using the Delta Lake, I recommend you click on these links because they will show you what it is and how to use it, and I think it has opportunities to greatly speed up your workloads. Okay, finally some code. I'm going to be working with the TPC DS dataset. Raise your hands, how many people know what that is? Okay, so it's basically a benchmarking dataset that you can create for sizing at any size you want. I created a 1 terabyte dataset to do stress testing on and whatnot for this demo. And this is what this is doing is just taking store sales and joining with date, item, and inventory. Kind of a common thing you would do if you're in a retail kind of organization. And that's all this does. But it is a 1 terabyte dataset, so this is going to result in some significant work. We're going to use this for the next few slides. So I know this, let's see how, yeah, you probably can't see that, but just trust me when I say that says 6.2, the top one there says 6.2 hours. We have 0 of 200 tasks running, or we have 0 of 200 completed, and we have our 96 cores running. This is running this for 6 hours, and nothing's completed yet. We read 60 gigabytes, probably pretty fast. If you were refreshing that probably only took a few moments to read that. But I didn't do any lazy loading. I just ran this query, and here we are 6 hours later and a lot of money, and nothing's happening. I don't know when it'll finish. This is pretty common. I see this sometimes. And if you're at this point, add the lazy loading. You're going to have to find a way to parse down that data set a little bit. So a lot of people say, well, there's this shuffle partition thing. Let's just increase that. So instead of using the default of 200, let's go to 2,000 something partitions, and let's try that. A lot smaller data per partition. Maybe we'll get that to work. Well, I tried that for another hour, and still made no progress, although I read less data, so okay. So now what? Well, that's the thing. If I just simply add that Hive partition pruning filter, I can now complete the entire job with the default 200 shuffle partitions in 8 minutes. So this is why I wanted to make sure and cover this base. If you don't know what you're doing as far as Hive partitioning or partition pruning on your joins or making it simple for your BI analysts, it's absolutely critical that you do, okay, for this reason. If you don't know whether or not you're successfully using the Hive partition pruning or whatever kind of partition pruning you're using, data skipping, you can go into the Spark UI. Remember all those blue boxes? Well, here we're going to dig in a little bit. That first number there says the number of files read. Okay, 1,823 on the left, and on the right, 730. So we were able to minimize down that amount of data significantly by over a half. And so in so doing, that Cartesian product in the middle was so much smaller, it was able to complete. Also, if you are a developer, I'm glad to see how many people raise your hands that you are using this all the time, because that's fantastic news. That means that you're probably actually doing some things right here. But if you don't know what all these crazy numbers are in here, I suggest you read them very carefully and get to know them, because this is what is going to allow you to really optimize those crazy charts. And hopefully by the end of this session, you'll know how to use a lot of these, and the ones that you don't understand yet or still don't understand, you can ask the community and find the answers pretty quickly online. Okay, now let's get into actual optimization, not just Hive stuff, okay? So what's a partition? Big data. The Hive world ruined us in Spark because everyone thinks that a Hive partition and a Spark partition are the same thing, and yeah, they're not. Okay, a partition is defined as a number of portions into which some operating system divides memory or storage. Okay, so really it's a subset of a superset. When you take a partition of something, it's just a subset. In storage, when you take a folder of a table, right, in Hive, it has a folder, and when you take a subset of that, it's a partition. You can configure it such that it's a partition, a subset. Well, when we have, let's say we have a CSV, and we want to break it into partitions, what does that mean? We're just going to take subsets, right? So if Spark's going to read in 30 partitions, well, that means I broke that CSV into 30 pieces. And remember I told you that tasks are going to do the same thing, just on a different segment of data? So that's what a Spark partition is. The rest of this talk is going to go into the deep dives of how to use these partitions and how to size them correctly throughout so that you can actually make this work and make Spark efficient. So it's really important to know that those are not the same thing. Furthermore, Spark has three, they're unofficial, they're Daniel's idea of what Spark has as partition types, but I call input, output, and shuffle, which this makes a lot of sense if you think about how a lineage of a job works. You read data in, you do stuff to it, and then you write it out somewhere, bring it back to your screen. Well, the reason that people, for lack of a better term, suck so bad at sizing all these right is because it's hard. The input and the output are sized, are controlled by the size of the partitions. But the shuffle in the middle is changed by the count. So naturally and unfortunately, we have a little math to do to figure this out. So talking about, let's start with output, okay? Most people get output partitions pretty well okay, because if they don't get it right, it becomes pretty obvious. The next stages fail because they have small files problems, or they're too big, or the writes take forever. So they usually know it's pretty obvious when you have a wrong output because you see the files. So Spark, on the input, does a pretty good job of sizing it right, assuming that you have proper compression and proper input data. Spark does a pretty good job of sizing those input partitions, which defaults at 128 megabytes. Okay, so Spark tries to change those, or pull in and bin pack to 128 megabytes. Where people seem to just have forgotten how to optimize Spark is on the shuffle. And it seems to have never been clear, so I want to make it clear today. Okay, the default for a shuffle is changed by a count, and it's controlled with this flag, Spark SQL Shuffle Partitions. The default, for some unknown reason, was set to 200 when it was built, and I've asked people that built this, and they don't remember or know why, even on the PMC, why it's 200, but it is what it is. And yes, we've tried to come up with ways to use machine learning and stuff to change this appropriately. There's a lot of deep, good reasons why we can't do it yet, but it's wrong, okay? Your workload, if you have 200 shuffle partitions and you have more than 20 gigs of data, this is a wrong number. Now you can go home and fix it. Okay, it's wrong, it's wrong, it's wrong. So you got to change this. How do you change it? Okay, I'm going to give you an equation. This equation will help you get this number correct. The shuffle partition count should equal the shuffle stage input size divided by the target size that you want your partitions to be. What should that target size be? Well, that target size should be less than 200 megabytes. I usually try between 100 to 200 on my median size for my partitions to be 100 to 200 megabytes. Okay, so let's do an example because that is fluffy stuff. So let's talk about an actual example. We have some data. We see a shuffle partition come in at 210 gigabytes. All right, we're going to set our target size to 200 megabytes because Daniel said so. And that's going to be 1,050 shuffle partitions. So we're going to go ahead and change that configuration to that number, not 200. 200 would be wrong. But if we have 2,000 cores, then 1,050 is also wrong because we want to utilize our whole cluster. And so maybe we would actually set that to 2,000 if we had 2,000 cores. There are other reasons you might not do that, but let's just assume you wanted to use the whole cluster and the cloud provider could write at infinite speeds. So we would put that to 2,000 maybe. So let's go. I'm going to do everything they tell you not to do on a slide because I'm a rebel. But let's assume we have 96 cores. No, that's not work. So we have 96 core cluster, and we're going to read in some data. And I'm going to use the mouse here because this might help. Let's see. Yeah, this will work. So we have a shuffle data. We have this 96 core data set. And we have this is when I said what your input shuffle size is, that stage size, right here you see shuffle read of 54 gigabytes. Can you guys read that a little bit? 54 gigabytes is your input shuffle read. So if you take that 54 gigabytes and you divide it by the default shuffle partitions of 200, you're going to get about 270 megabytes per partition. And that's a little bit bigger than what Daniel said was the right number. So it's a little bit bigger, but it might not be that big of a deal. But actually, if you dig in and look a little bit closer, you're going to see that the shuffle spill and shuffle spill to disk and memory. When you see that, you got the number wrong. Go back and try again, especially if you're seeing it somewhere outside of the max. Like maybe you have a little skew in your data and it's not worth engineering it away. So you're going to allow it, but you have to make that decision to allow it. And you should, if you see this where your median is spilling, your median quartile here is spilling, that means you need more partitions, basically. So go in and try, and if you have that closer to 200, you're much more likely to not have any spill. Now, if you've cached everything, since up to this point you might not have enough working memory left, so you might still spill. But generally speaking, that's a good target. Now, if you wind up in a situation where you're trying to do this, oh yeah, I forgot my little arrows. Thanks. So if you wind up in this situation, you probably aren't going to get this stage to complete, so you're not going to get these perfect numbers because you're going to say, okay, well, it's cranking and it's been cranking forever and I don't know, it's not finishing. So how do you tell what the input size is to do that equation? If we take a look at this DAG right here, you can see that that stage 19 and 20 are feeding stage 21. And so if we go down to the Spark UI and we look at the different stages, we look at 19 and 20, we can actually sum those together and know that that is going to be the shuffle read size of that first shuffle stage. So even if that shuffle stage can't complete and you can't get that number, you can sum up the input stages so that you can actually see what the read of that stage that's failing is going to be and then work that equation out. That's a lot of numbers. This is on YouTube, so you can go back through it slower if you need to. But we're gonna have to go a little fast, sorry. But let's try this again, right? So we had 270 megabytes, which isn't too bad, but we used the default of the wrong 200 shuffle partitions. What if we went to the right number? And in this case, I'm going to say 480 is the right number. Well, how did I get to 480? Because I broke my own rules in a lot of ways. Well, I did, but the reason I went to 480 is because I said, okay, well, I want my target shuffle size to be 100 megabytes, not 200. And why did I pick 100? Well, if you look here, you see that my actual size of my read was 54 gigabytes, but you can see that my shuffle spill here, and maybe you can't read it, but right here, my shuffle spill is about 550 gigs to memory. That means that my columnar compression was pretty good, which means I had a lot of redundant data. So I'm going to blow out a little bit more in memory than I normally would. So that number 200 might need to be scaled back a little bit since I'm obviously getting a lot of columnar compression. So I chose 100. And like I said, less than 100 or less than 200 is okay. I saw that, so I went to 100. Now, I say, okay, well, I have 54 gigabytes. I'm going to divide that by 100 megabytes, and I'm going to get to 540. Well, why did I not use 540? Because that would be my equation. Why did I pick 480 instead? Well, now we need to go back and look at the parallelism that we have available in our cluster. If I took 540 and divided that by our total core count of 96, then that would mean that I have 5.63 batches to work through before I complete my job. And you can see at the bottom there that my duration is about 1.5 minutes for each task. So if my duration takes 1.5 minutes and I get the first batch, as I get done with my 4th batch and enter my 5th batch, only 63% of my cores are actually operating in that last batch. So because of that, what is that, 30-something% of my cluster is no longer being utilized. It's just sitting there for 1.5 minutes at least while that last section of data is being taken care of. So instead, I'd rather keep them all running at the same time at maximum speed, so I go to a 480. That's how I got that number. Okay, so that's shuffle partitions in a nutshell, and we'll take questions at the end if you have them. I'm sure there's plenty. But let's move on to input partitions. So we got our shuffles done. That's working, but now I've got some issues on my input partitions. Now Spark generally, like I said, does a good job of taking care of these input partitions, but sometimes it doesn't. And there's a lot of reasons why not. Let's say I have a really big cluster. I'm going to do some really heavy computations on this data. So I have 200 cores, but I only have 200 megabytes of data. Well, because I have 128 megabyte default input partition size, I'm only going to wind up loading in like maybe 2 partitions. So I don't want to have 200 cores with only 2 tasks, because now I'm only going to use 2 cores. So I have 198 sitting there with nothing. So in this case, I want to size my input partitions down to 1 megabyte each. So I would simply change that parameter, max partition bytes, down to 1 megabyte instead of the default 128. And that would make that data originally read into Spark across 200 partitions, not 2. The next reason is heavily nested or repetitive data. Because that, as you just saw a moment ago, that can blow out a lot in memory. If you're not doing a shuffle or if you can't handle it somewhere else, that repetitive data can really get big in memory. So you might want to scale back your input size. The next one is generating data. If you have an array and you're exploding it, or you're generating a lot of data per key or something like that, that's going to obviously create more memory. So you need to have smaller starting segments so that you can actually write more data, or I'm sorry, have more space for the extra data. Also, there's a lot of issues sometimes with the source data. If it's like a bunch of arrays of structs of arrays and they have a really big skew, you might need to shrink that down because that also might blow up in memory. And then non-vectorized UDFs. We'll talk about this more at the end, but non-vectorized UDFs, because they can't be fully serialized in tungsten, and because they come out of tungsten and go to row compression, those are actually going to take up a lot more memory. So we'd want to size this down maybe if we're using non-vectorized UDFs. So let's take a more concrete look at what I'm talking about. So this first one here you see at the top, that's using the default of 128 megabytes. And I have this data source I'm reading. And when I first read it, I'm going to just use the default, and I get 90 partitions. You can always figure out how many partitions a data frame has by using this line 3 there, rdd.partitions.size. And so now I have 90 partitions, but this cluster has 96 cores. So maybe I want more than more partitions, or maybe I have 1,000 cores or something, right? So I'm going to size that down using that next section there, and then I get 710 input partitions rather than the 90 I originally had. So what does this do? Well, I had 96 cores, and I was able to reduce my time by about half just by changing the input partitions, because there was no shuffle, so there was nowhere else for me to really change anything. So what I did was read and write, but by using all my cores and sizing that down, I was able to read and write a lot faster. Okay, output partitions. There's a lot of reasons why you might want to change this. Well, really about 2 probably. But when you're writing out data, you want to either change the size of the files or you want to change the composition of the files. So if you want to change the size of the files, you have a couple different ways, either coalesce or repartition, which we'll talk about in a moment, or you can maybe rebalance the data on the output so that there's not so much skew, and repartition it like that. So that would change the composition. Again, let's talk about an example. If you want to write data 15 gigabytes approximately, but you want to average an output file size of 1.5 gig, because that's what your boss told you was a good number. Well, now your maximum write size partition, your parallelism is only 10. If you have 96 cores in your cluster and you only have 10 writers, 86 cores are sitting there idle during the entire write. So what does that look like? Well, if we go into this workload and we said my boss told me I had to have 1.5 gigabyte files, okay, cool. That takes 15 minutes and 86 cores are idle. But Mr. Boss, if I do it this way and have 160 megabyte files instead, now I'm going to be able to write this out in 1.8 minutes, utilizing the full cluster and save us a lot of money. But he says he wants 1.5 gigabytes instead of 160, but he wants me to do this too. Okay, great. Now how? Well, what we should do a lot of times, and this scales, right? I mean, this problem gets bigger when the data gets bigger. What we should do is use a lot of cores and write as fast as we can initially when we do the operations, and then come back later with a smaller cluster to do the compactions that we need to do later so that we don't just waste all those compute cycles when we don't need to. When we have those big clusters, we want to be using them. Okay, we're going to take these one at a time, but this is really the last part of partitions and really the crux of how you actually manage your jobs. So bear with me here. The first is the write option. Probably don't use this unless there's some weird case, some special case. This changes the records per file, but as you can imagine, that probably isn't going to help you. How many records make up 1.5 gigabytes? I don't know. So I'm not going to use that. The next one is coalesce. They tell you to use this all the time. That's fantastic. You have 2,000 shuffle partitions, cool, but you want to get down to 1.5 gigs, so you're going to coalesce back to 10, and okay, you got your 1.5. But I had a big shuffle stage before that write. So what happened? Now I have 2,000 cores. I want to do those. I want to use 2,000 cores to do that heavy computational algorithm or whatever. But I need to write out to 10 files, so I'm going to coalesce it right before I do the write. What happens though is that coalesce gets pushed up into that last stage, and now you only have 10 cores doing that heavy computation. Dang it, I broke it again. I broke Daniel's equation, and now my job's spilling everywhere and it's breaking. Why? We'll talk about that in just a second, how to fix that. But yes, coalesce, anytime you want to go down in the size, coalesce is how you should do it. The next one is repartition. I see people that don't have a clue how to use this all the time. So if you're using it, probably don't, or at least think about why you're using it, okay? There are valid reasons to use this. But don't use it to minimize, to shrink the number of partitions. Always use coalesce, unless you're trying to rebalance the output. If you don't know what I'm talking about, when you do, it'll make sense. But you should only be repartitioning to go up in the size of the data. So if you can't use Spark input partition sizing to change the size of your input so that you can scale out, maybe you would need to do a repartition to get more partitions that go across your entire cluster. But unless that's the case, or unless you're trying to rebalance the data, there's no reason to do a repartition. And so people think, well, what if I repartition right before I do a join or a group by into what I'm grouping by? How are you going to know how many different partitions that next section is going to be broken into? You don't. There's no way you're going to actually, I won't say there's no way. There's a very improbable likelihood that you're going to successfully repartition the way that Spark needs it repartitioned before the join. So you're just going to wind up adding a full shuffle before the join of the group by. So don't try to repartition. Let Spark do that. So don't call a repartition by key or by group by or whatever, and then call your group by, because you're just going to add a whole shuffle. So this is why I steer against repartition, is because it does require that full shuffle. It moves all the data around. It's really expensive. And what people a lot of times don't realize, especially if they don't know what shuffle partitions are, is that you can just change the SQL shuffle partition size and actually make it so that you don't need to repartition into something so that you get a number of writes. For example, if I want to write out 200 files, if I change my shuffle partitions to 200, I'm going to probably write 200 files, because usually a shuffle feeds a write. Right? So then I would have 200 partitions that are ready to be written. However, as that example, whenever you get in the real world, that example I just gave where if you coalesce, it's going to push that up into the previous stage. If you think about that, I have 3 or 4 or 5 shuffle stages throughout my job. 2 of those earlier ones are those really big ones. And I need to reduce, I want to use all my cores on those. But now the last shuffle partition, the last shuffle stage doesn't have hardly any data in it. So now I have my 2,000 shuffles, 2,000 shuffle partitions, and now I'm writing 2,000 small files. Okay, but now when I try to change that, my earlier stages are now breaking because they're not big enough. So what we have to do in this case is coalesce will break the last stage or the earlier stages. Shuffle partitions will break one of them. So what we have to do if nothing is working, because of the lineage of the job, is to create what I call a stage barrier. Okay, you have to break that lineage apart, and you can do that with checkpoints. So a normal checkpoint will checkpoint out to S3 or whatever location you want, but it is going to require a full write to the cloud provider, right? So instead, you can use a local checkpoint to bring it down to a local disk, and hopefully like a RAM disk or SSD, write it to that local, just call local checkpoint, and it'll put it right on that SSD. And then it'll read it back in, and now you can call your coalesce without breaking that last stage, okay? This is probably not right for production, because in production, this will actually, this can cause failures, and depending on how much is on the disk, and if you're on shared clusters, this will probably also break, so you might need to do the resilient remote checkpoint. But another way to do it is to just write down to Parquet and read back. We want to avoid writes where we can, but in this case, you have nothing better to do because you need the big shuffle stage early, but you can't have that many writes at the end. However, yet we broke out another thing, because now we're writing the right number of shuffle partitions. We're writing 2,000, but we're writing that out to Parquet, out to the local or to the cloud provider, but now we're denial servicing it. So how do we win? It's really hard to win this battle, so you're going to have to kind of play with it, and you might actually have to size your cloud provider writes down a bit so that you don't denial service them. And the last thing, if you're on Databricks or if you're using Delta Lake, you can use an optimize in the middle, an auto optimize. I think that requires Databricks. I don't remember, but if you have Databricks and you can use an auto optimize, that will automatically create that stage barrier for you. Write it to a local disk safely, where it can also be recovered, and then write it out to the cloud provider in batches of the maximum that the cloud provider will allow. So basically, it'll test higher. And then if it starts getting failures from the cloud provider on write speeds, it'll back off. So that's a really smart way to do it, and you can write that yourself. It's just really complicated. So that's one of the benefits that Databricks does have. But usually it doesn't get this complicated, but I just wanted to walk you through all of the ways that it can be challenging and ways to fix it. Okay, so here we are at about half the talk, right? And I just talked about partitions. Why did I spend that much time? Because I think about half of you can probably take what I just said and go home and fix your workloads. So hopefully that's true, and hopefully this will help. But now we're actually going to talk a lot about the advanced optimizations coming in this next section, okay? So the next piece, we're going to look at the way to find imbalances in your data sets and in your workloads, how to actually properly use persist and cache, how to optimize the joins, how to handle skews, which operations you should look for in your code bases to remove, how to use vectorized UDFs and what that means, and then if we should have time at the end to do multi-dimensional parallelism, which is actually a pretty cool concept that Spark enables out of the box. Okay, so in any parallel compute world, you have to have a balanced, you have to have an equilibrium of all your resources, including your data, your compute. Everything needs to be balanced, or you're going to wind up with hotspots or imbalance, and it's going to be slow and lagging on that one area. So especially when we talk about task duration and partition size, that's why I spent so much time on that, because those all need to be, you have to find that balance over there. And in this case, we're going to talk about skew in a little bit. Skew is obviously one of the ones that happens all the time for us. And how many of you have got this amazing job that you wrote just to wind up, and it's so fast, up until the last partition, right? Yeah, that's what I thought. Me too. Yeah, it sucks. So you wind up sitting there, now what? So what do we do in this? I call that a straggling task, and that's usually a pretty good sign that you have data skew. It could be a bad node or some other issue, but usually it's data skew. Okay, if we want to confirm that it's data skew, we're going to look at the 75th percentile to the max, maybe the median to the max, and just look for that sharp curve. If you start to see that curve, you're going to be able to say, okay, for sure, this is data skew. Some of my partitions are much bigger than the other partitions. So for one core to complete that big partition, it's going to take a lot longer. But not only is it going to take a linear amount of time longer, it's going to take an exponential amount of time longer because it has to do all that spill, which is exponentially inefficient. So as you get bigger spills, it gets even more inefficient. Oh, and you can see that at the bottom. When you see that spill at the end there, like those big spills just on the max, and they get too large, you just stop the job, try again. You got to figure something out because it's not going to work. Let's talk about persistence before I go deep dive into Skew. I don't know how many times I asked this on interview questions or whatever, but like cache and persist, they're the same thing. But persist allows you to change the types of caching that you're doing. So instead of just doing it in memory or memory on disk, you can do it other ways, like just to disk. So maybe you want to do it on disk only instead of just in memory, etc. So a cache by default is memory and disk. So use up the memory till I get to that 50% or whatever that threshold is for storage memory. Once that's taken, now go to disk. There's some other ones I'll let you read through. I left the link there. I suggest that you look at them because they can be useful in various workloads. But know that persistence is not free. You don't just cache stuff and then it's faster. I mean, yes, it is. But if you're only going to read it one time, there's no benefit to cache it because I'd rather cache it to do the work I need to do rather than cache it and then serialize it into memory, put it in memory, and then go get it from memory, read it back in, and then do my work. Obviously, it doesn't make any sense. So what we need to do is we need to find repetition because we need to bring the data where we're going to use it a lot of times. We'll spin the extra cycles that it takes to put that into memory, and that's how we're going to use. That's how we're properly going to use persistence. And then I know I'm a developer too. We're lazy. We don't clean up after ourselves because garbage collection has spoiled us. But make sure you don't forget to do a df unpersist. When you write a cache in a production workload, when you're working in any kind of actual production-ready code, make sure you call the unpersist to destroy that in-memory object. Because remember, the storage memory takes up half of all the memory. So if you use all that cache stuff, and now you're minimizing and taking away from your working memory. So if you can expand that working memory, you're less likely to get spills. Okay, back to this fun guy. I'm sure that you can find the problem here, right? You can see what's going on? Well, actually, I think you're probably laughing at me thinking I'm joking. I'm kind of not. You can find opportunities for persistence here. So if you really start to look at this, you can start to see some patterns. And there's actually some that I don't have highlighted. Now it's our job to dig into these different synonymous branches, if you will, and see if there's opportunities for caching. Just because they look the same doesn't mean I can find a superset that I can cache, but it might mean that I can. So where I'm doing a lot of the same work over and over again, maybe I could do that work one time earlier up in the DAG, cache it, and now have it available for everything else to read from, rather than reprocessing all of that again. Not necessarily for sure, but maybe I can. So look for that. And what I always do, as I told you, is I zoom all the way out on that SQL plan, and I try to find what I have that looks the same, and then try to find a superset that I can cache from which all these other sections, the subsets, can read from. Also, another thing is there's this DBIO cache. If you don't know what it is, it's another type of caching, and it is for Databricks only, I believe, but it is extremely fast. So I wanted to put this in here as a plug just because if you are on Databricks and you're not using DBIO cache, extremely important that you do. You're just leaving money on the table. Make sure you go home and read about it. I'm not going to go into a lot of detail on it. It is extremely fast. And then it even has the ability for like BI workloads where you can say cache select and then some subset of your data, which when the source data changes, so maybe I cache select read from a JDBC table. When I do that, if the JDBC table changes, so shall my cache data set. So that means that any BI tools that are reading from that will automatically get that new data set and it will always be hot and ready to go. So that's a really great way to use the DBIO cache. But there's the configuration at the bottom on how to set this up. If you're not using some of the default machines, and like I said, this documentation is there. And the way that you can know for sure you're using it is right here. You'll see the Parquet.io cache in your Spark UI under Storage tab. All right, join optimization. This is probably where everybody came to this talk for. So the slowest but the most stable join is a sort merge join, right? We all know that probably. It's a really fast optimization if I can just do a broadcast join, which I'll talk more about in a moment. But there's also skew joins, range joins, and then the beast from hell, which is the broadcast nested loop join, which I'll talk about briefly here today and how to get around it if you can. So the first one is the sort merge join when both sides are big. If you can't broadcast either side, you have to use that sort merge join. Not bad, but it is expensive and it takes a while. So if you can minimize that, fantastic. The broadcast join is a map side join for the Hive people. It takes one side small and you can broadcast it to the cluster so that it's like an in-memory local hash map lookup. But there are some risks to doing this. If you force it, using the broadcast hints and stuff, you are very likely to kill your production workload at some point. So you're likely to need to do some kind of function that does a check to validate that it's okay to broadcast this data frame before you do it. I can't tell you how to do that today, but make sure that you have checker functions that are looking at those data frames to figure out how to do that, that broadcast. Because if you don't, you can crash your driver because you pulled too much back, or you can hit that 4 GB max threshold by default. You can increase it too. But then you can also run out of memory. So if you, and this is a cumulative broadcast. So if you have, maybe in your lineage, you have 6 broadcasts, that's the cumulative sum of all of those broadcasts that have to fit into memory. So let's work through this a little bit. I'm leading up to an interview question that no one's ever gotten right, even after I did this talk in the States. So we take a data set from the data lake and we read it in to persist it. So let's say it's 12 gigabytes. We have 6 partitions and 3 executors. So that means that each executor is going to get 2 partitions. So in memory, when we persist the data frame, that takes up 12 gigabytes still, the same as the original data set, more or less. However, when we broadcast it, it actually takes maybe this same data frame broadcast will take between 48 and 60 gigabytes of memory, assuming a perfect a perfect compression ratio, which you don't get that either. So it'll be more than 48 gigabytes of memory required per node, because what happens is the data lake breaks it up into partitions, then it goes through the original persistence cycle. So it persists that, moves those different pieces into memory, but then the driver then collects all of that to the driver, converts it to a hash map, which this is where you lose the compression ratio, because now your 12 gigabytes became 100. So now your driver has 100 gigabytes to send out to all of the executors. Let's just stick with 12 now to keep it simple though. So now we send out back to 12 gigabytes to each different node. So now each node has a full copy of that data frame in a hash map type format that's no longer greatly compressed. So that's why we always have to be careful. Just because we have a lot of memory on our driver or a lot of memory on our executors doesn't mean that we can go broadcasting 2 gigabyte data frames, because it's going to wind up being 100 gigabytes on the node. So we'll take an example. If you don't believe me, on the left, that's 96 gigabytes being joined up with 126 megabytes on the right. So when you see on the right here, 126 megabytes is getting a sort merge join, and it literally says 126 megabytes there. But the same query, when I do a broadcast join, blows up into 270. Again, it's just the compression ratio between row and columnar and the way that the in-tungsten in-memory compression ratios work. So you have to be careful, because these can blow up several times, depending on the redundancy of the data and a couple other factors. But the way that you force it is, if you are bold and you have the proper validation functions, in production, if you want to broadcast it, you can with the validation function by putting a broadcast function. It's in the Spark SQL functions library. And you can just broadcast that out, and that will force it to do it or crash your system. In development, I do this, and I don't care, because I'm the only one on the system and I believe in myself. So I think I can do it. And it's no problem if it fails, it's not a big deal. But in production, you got to be careful here. So a better way to do this is to set a parameter, and I believe I have it here. There's a parameter that I think we'll get to. If not, remind me and I'll tell you later. But there's a default broadcast join size, which is by default set to 10 megabytes. Okay, that's the default. You can increase that, and if you have a lot of memory and you're doing one production workload on this cluster, you can increase that to 40 or 50 or maybe even 64 megs. Safely, and then everything that can be broadcasted that Spark can identify, it will broadcast up to that size. It's the default auto broadcast join threshold. That's the parameter. So you can look for that. Otherwise, you have to use this method here. So if we go back to our first workload that never finished after 6 hours, this is the same query yet again. I just added the broadcast in there, and I don't even have it with the 480. I just back to default 200 shuffle partitions. But now instead of 6 hours or 60 minutes or 10 minutes, we're down to 2.5. So add a broadcast, proper partition pruning, we're down to 2.5 minutes. But now let's go back to where we had the task that never finished. This is what happens. This is a skewed data set. If you look at the count on the right, we have like 42 million records for each of those keys on the left, and then after that we have 20. So sometimes these will all wind up on the same core, and so now one core is responsible for 99.9999% of our data, which is not, now we should just do it on our local machine. So instead, what we're going to do is we're going to fix that by redistributing it. There's really two ways. There's an easy way with Databricks, and then there's a little less easy way with salting in open source. So let's talk about Databricks really fast because it's easy. I have a link in here for more documentation if you'd like to see it. But basically what you're going to do is identify a hint inside of the join called a skew, and then you're going to then tell it which key is the skewed key. In this case, the skewed keys are the first 3 IDs there because it's a composite key. And then if I stop there, then it's going to redistribute all of those keys. So it's going to take a lot of time to sample and rebroadcast, or like rearrange all the keys on the left. However, if I can tell it which keys are skewed, give it that list of keys that are skewed, it'll only redistribute those. And it won't spend time on the rest of the keys that are well distributed already. So what I normally do is I do this count, and I'll look at the graph of the counts, and I see the elbow, right? Sometimes there's this big elbow. It shoots up to some massive count like right here. All those keys over here, I grab those, and I put those into my skewed keys, and now my skew join works fine. You can create functions for it. There's plenty of functions available, and I think there's one in this posted in this presentation on the notes section, so you can download it and look. The next one is like a group by or a join, but especially a group by where you have to do salting because you're on open source Spark or you're somewhere that you don't have this hint. And so in this example, let's think about something like we got 3 cities. Well, I'm not really good at European city sizes, so let me just go with United States city sizes. Hopefully you'll know these. New York City, Los Angeles, and Fargo, North Dakota. For those of you that don't know Fargo, North Dakota, it's a small town. The other 2 are big. So this is what we typically wind up with when we have a group by that's going to wind up with a big skew. We're going to group by the city and state. And obviously, those 2 big ones are going to have a lot, or take a lot more. And maybe we have a lot of other cities, and obviously there's a few big cities and a ton of small cities, right? So if this happens, we're going to wind up with those 4 tasks not finishing ever. And so what we're going to do instead is we're going to create a random value. That's going to be like a noise. We're going to call it noise. We're going to create noise so that we can better distribute that data equally. There's books on this on how to do salting properly. So if this interests you, I suggest you look at them. But if you get you can call this random function here from Spark SQL functions, and use this here. And if you just use this new format here to introduce that noise, and now group by that salt key as well as the original 2 keys, because that salt key is random. But random and bound by the number of cores you have, you'll be able to distribute that equally across all your cores. So notice what I did here on the top. That shuffle partitions that I told you about earlier, I went ahead and I got that number. So I'm assuming I set that correctly earlier. And now I'm going to grab that number and subtract 1 to know how much noise to bring in so that I equally distribute across all my shuffle partitions. Okay? Okay, for the beast. A lot of times this comes from complicated join logic where you have for everything on the left do something on the right, or you're looking for commonalities between complex joins, or something like that. So if you have those tasks that never finish, or you have a job that kind of never starts, go to the SQL tab and look for this. If you have it in there, if you're doing complicated join logic, you might wind up with this. And that's okay. Sometimes you actually need this. But if you have a very big data set, it's unlikely that this is going to work. So you're going to need to pare that down, break it down, or find another way to do it with cleverness. So sometimes, though, especially in SQL, we wind up with these broadcast nested loop joins because of a user error. The user error is something like where you have a SQL join, or I'm sorry, a SQL where not in something else, And here it's even worse because it's a select distinct, where not in, select distinct from something else. That not in function in SQL, or I'm sorry, in Spark SQL, is probably shouldn't use it ever. It works sometimes, but also it can lead to this. So instead, what's better, you notice that stage took 7 minutes. It did finish, but we did two things in the bottom one that made it a lot better. We went from 7 minutes to 16 seconds by simply doing two things. Instead of where not in, we just put where not exists. Okay, so where not exists function is much more efficient. And you'll notice the equal sign there has the little greater than less than's around it. That means that it's a null safe join. So when we or a null safe equality. So that means that it's not going to calculate the Cartesian product between the nulls on both sides. So that's going to go a lot faster too. If you wind up with these and you don't need to calculate the nulls on both sides, or you don't need to join the nulls, either filter them out first or use this so that you can get around joining nulls, because it's it doesn't work. I'm not going to dig into details on the range join optimization today. It's pretty deep and it's pretty specific. If you're doing time-based analysis or whatever, yes, you probably have this problem in a lot of ways. There's a lot of good documentation here under this reference tab, but there's several different kinds of joins that are range type joins, and usually it's an inequality join where on one side you're saying greater than or less than this. Basically, join with this key where it's in between these other two sections. So that's a point in an interval. Other one is like a point in overlap. If you have like a Venn diagram and you say, okay, well, everything that's this and greater, join that. And that can wind up with extremely skewed data sets, but not just skewed, but also where you have some sections that are much bigger than others. So for every join key on the left, I have to look for this entire table on the right. So this is usually fixed by binning. Databricks has a range join hint. You can just set a bin size, and then there's a whole detail write-up on how to select the bin size, and that will fix it if you're on Databricks. Otherwise, you're going to have to read the documentation a little more carefully and identify how to do the binning yourself. But essentially, you need to do binning on both sides so that you don't have to scan the entire right-hand side of the table for every key on the left. Okay. The next section is about getting rid of expensive operations. When I go to a client, I a lot of times will just do a Command-Shift-F in their IntelliJ and IntelliJ on their project and start looking for keywords. And this will probably save, I don't know, 20 to 60% of the runtime because they're using repartition wrong or these other things. So again, like I said earlier, go look for those repartitions and see if you actually need them. Take them out. Might go faster. It probably will, unless you're using them for a very specific reason and you understand why. The next one is count. Data scientists are the best at this. They like to count after everything to make sure that the numbers and the shapes are right. I get it. I do too. I like it. But when you go to production, though, don't forget to cut them out. Don't send all those into production unless you really need them. And now we've got MLflow, and it's even gotten worse because everybody likes to send them all to MLflow at every stage. Okay, if you really want to, but just know that's going to be a little expensive. The next one is distinct counts. There's this function called approximate count distinct. You can tell it the margin of error that you'll allow, and that will go from maybe 20 minutes to 20 seconds or less to calculate the same thing and be within 2% error. Now, I know, especially in data science and other areas in banking and other areas, there's no allotment for this error of 2% even, but a lot of times 2% error is fine. You're looking for a ballpark on something and you're not needing an exact count. If you don't need the exact count, absolutely please use the approximate count distinct. It'll save you a lot of time. If you have to use a distinct count, make sure that you're only distinct counting what you actually need to distinct count. So make sure you do this before you do your joins. Don't join a whole bunch of duplicate data and then do a distinct count because now you've had to do it. We try our best to push these things up in the DAG, but we don't always get it right. So just make sure you drop duplicates before the join, before the group by, and also, or use a distinct before that. Also, I don't like to type much if I can avoid it. So instead of .distinct and then the columns that you want distinct, we're a lot of times too lazy to do that before the join because we have so many columns. Well, instead, you can just drop duplicates and then put in the columns that you want to drop on. So use the inverse of the distinct. So I encourage you to look at that if you haven't used that before. It's pretty valuable. Okay, UDF penalties. Scala UDFs are pretty fast. Python UDFs are not very fast by default, and like the R UDFs sometimes work. But if you can vectorize them on Python, then they're probably faster than the ones in Scala, ultimately. So this is an example below on the throughput here. You can see the different values. If you think about subtract mean or the cumulative DF there, you can see the differences by using vectorized pandas. Vectorized UDFs versus the regular Python UDFs. So if you're in Python, I highly encourage, like, don't ever use another UDF. Use vectorized UDFs if you have to. And we've made it pretty simple now. I've put a lot of links on here for you to go and dig into all the details. But if you can do an app pandas UDF, you can pretty much do anything you want, but you can parallelize it and it'll be serialized and byte encoded. So it'll be much, much more efficient. Also, if we can, just avoid it completely. There's a whole lot of an ever-growing number of functions in Spark SQL functions which have already been vectorized for you. There are very advanced functions in there, like complex functions such as array and other things that will get you a lot of value. I forget what they're called. They're called composite functions, something like that. Yeah, I know you guys know. Yeah, forgetting it. Anyway, those functions are very valuable, and I think that if you click on that link, it takes you to the list of those functions, and there's a notebook attached that shows you all those very valuable functions as well. So try first and foremost to use those functions in there before you write your own UDFs. And a lot of times I see people say, well, I want to write my own UDFs because my code gets all cluttery if I don't. Okay, that's fine, but still use Spark SQL functions. But what that means is I take in, you define your UDF, but it should take in one or many columns, do columnar logic, and then return one column. So now I say with column, and I call the function, and say column A, B, C, and D are my input columns, and I do columnar logic on it, and return one column, and now I have the answer to that output of the UDF. But the UDF's never left column format. So that's one way to clean up the code without going into scalars. What you don't want to do is go into primitives, right? You don't want to have ints and strings if you can avoid it. That's what we try to avoid unless we're in a pandas UDF. Scala's getting a little bit better with the default functionality of UDFs, but still, just try to avoid it if you can. Oh yeah. Okay. So now the fun part. I got a few more minutes here. I want to talk about this. This is where things are probably going to get a little exciting. So I call this multidimensional parallelism. On Spark, we have 3 layers of parallelism. We have the parallelism on the driver because we have multiple cores. We have the parallelism on the executors because they also have multiple cores. And then we have the aggregate sum of all the executor cores, and that can be accessed to the Spark layer. So let's take advantage of all of them at one time. You can do this. Think about threading. And think about, in Scala, you can use fork joins, or you can use executor thread pools. But in this example, this is Scala, and I think Python 3 has pretty good support for safe parallelization, but Scala definitely does. And we use this all the time for things that we're doing in parallel. So what this does, let me walk you through this really quickly. First, we're going to do a fork join task support, and we're going to set some kind of parallelism. Maybe I set it to a certain number that my driver can handle, but that also that my executors can get through pretty quick. So the idea is to stack up all this work for the executors so that they know what they're doing next. In case I have one job that's kind of slowed down or I've got some skew here, rather than the whole cluster being idle, maybe it can go on and continue other work. So to do that, what I typically do is identify what I'm working on. In this case, years and months. So I have 2 years of data, 2018 and 2019, because my data is partitioned by year. And then it's also partitioned by month, so I get a range of 1 to 13, so 1 to 12. And now for each one of those, I want to, in parallel, compute them. So you can do this on multiple tables at one time if you're doing the same function across multiple tables, or if you're doing the same function across multiple partitions, you can also do it. And a lot of times, if you're doing pretty basic stuff, this isn't going to help you. But imagine if you wind up with something where you do my equation and you wind up with the answer tells you need 30,000 shuffle partitions. Okay, well, 30,000 shuffle partitions is probably going to crash your shuffle server. So what's better to do is do something like this, where you break up into like what I call maybe mini batches, and execute the same thing over many batches at one time. So I don't really know if I want to read this code to you, but I can give you a few moments to look at it. It's very helpful. And you can ask questions here in a moment if you don't get it. But essentially just creating an array, creating a parallelized array, and then looping through that on the driver such that the executors can operate on them in tandem. We do even machine learning like this. So we created an AutoML toolkit recently and released that into Databricks Labs. And that does all of the tuning and training on hyperparameter searches for the genetic algorithm in parallel on all of them using this exact example. Also, now with the advent of Delta, we're optimizing tables all the time. Well, these functions here will show you exactly how to parallel optimize all your tables. So if you've ever done an optimize, you realize that there's this long tail that just seems to sit there for a while a lot of times. Because this table has a partition that's a little bigger or something like that, or a file that's a little bigger. Well, instead of waiting, what I like to do is just stack up the whole list of all the tables in the on the database and say, okay, we'll do all this work and do it as fast as you can. And then it'll start optimizing all the tables and the cluster can shut down. This is much more efficient, I find. The trick is setting the parallelism number correctly. So it's got to be right based on the size of your driver and your cluster. So you might have to play with this in non-production for a little bit just to make sure that you get it, you understand how it works. But generally speaking, a safe number is, assuming you have a big enough cluster, the number of cores in your driver minus 1 is what your parallelism is a good number for parallelism. There's one other thing I'll call out, Spark network timeout. You might want to move that up a bit because if you have tasks sitting out too long that aren't getting operated on, Spark might think that that is a dead node or something like that and kill that task and resubmit it. So you might want to increase that a little bit, but maybe not get carried away. Okay, so that was a lot, I know. Thanks for sitting through it. I want to let you know that if you can do lazy loading combined with understanding your hardware, right-sizing your Spark partitions, that's one of the key ones, and provide balance to all the different sections. Optimize your joins, minimize the amount of data movement that you have, maximize the throughput via identification of repetition, and using vectorized UDFs, I think you'll be able to greatly increase and optimize your workloads. Thanks for your time, and I finished a little early, so I've got time for questions if you'd like. Go ahead.
Hi, thanks for knowledge level up. That was awesome.
Thanks.
I have mainly two questions regarding shuffle, partition size, and count, improvements. Yeah. So is that possible to do that automatically, like to get decompress size automatically to define?
Yeah.
Okay, I have this kind of executors and so on. And the second question is like continuation of first one. Like, is that all things are possible when we are working in dynamic allocation mode? Like how to get exact executor count and so on?
Yeah. So the first question around if I have this beautiful equation, why can I not just automate it? Well, the reason is because that trick of the input size, that shuffle stage input size, you don't get until it's too late for us to automatically identify. Trust me, there's been a lot of really, really smart people trying to figure it out, and if you can figure it out, please tell us. Because we've wanted to do that, and we've tried it, and that's kind of what dynamic execution was about, dynamic allocation was about, was trying to do that, but I noticed I never turned that on in production because it always fails at some point. And the reason is because knowing that input size requires that you understand your compression ratio. With the number of different types of data sets that we have and the number of different types of compression ratios and compression algorithms, that number is so dynamic, we can't get it right for Spark as a whole. You can get it right, probably, because you can know your data and you can build your own functions to do that, maybe. But we can't do it for the Spark world because there's too different. Regarding dynamic allocation, I say in development, that's fantastic, especially when you're new to Spark, but that equation will work. So once you get to know your data set, just use that equation. Dynamic allocation is okay, but when you go to production, I don't use it. It's not production safe, I don't think.
Thanks.
Yeah.
So I was waiting to ask a tricky question, but you partially answered it in the previous slides. We try to do the same things that you've described it with parallel stuff, but I think your slide is a little bit tricky because it seems it's possible to do this one, because this possible to do only with Databricks table, I guess, because when we tried to did this, I didn't see that cluster were fully utilized. For example, we have a 2000 partitions data frame which is persisted, and then after that we are trying to do to process load, filter, and persist some on 6,000 core cluster, so 2,000 partitions and 6,000 clusters. So theoretically, we can do 3 tasks in parallel, but now we can do like 2,000 and probably and a half.
Okay, so that's a good question. First of all, no, this has nothing to do with Databricks, proprietary, anything. This is just Scala, really, and it should work on any Spark. The key is identifying something that can be operated in parallel properly. So if there's independence between the two things, so right here, 2018 and 2019, and those months, those are independent, completely independent of each other. They're independent data sets. So nothing is required from one to the other. That's the key. If they are independent, then you can do this. I would suggest that clusters that size, that you might be hitting the cloud provider limits if you're doing a write. So if you're writing out from 6,000 cores, you're going to denial service your provider. So yes, you will not be able to do anything more than 2,000 cores is still too many. I say 1,200 is probably as much as you're going to ever write in parallel to either of the clouds.
Okay, thank you.
Yeah, I probably didn't answer your question very much, but it should work but I think your clusters are just too big. What you might try doing is writing, are you writing? Is the next step a write?
Yeah, next step, the last step is to write data.
Yeah, so if the last step is to write it, what you should try to do, I think, instead, is get some safe local storage, write it local. Mount a very fast shared local drive system. So on Databricks, it might be like /ml or some mount, right? That's on everything. Or your temp storage. If those are RAM disks or SSDs, right there, so that you can maximize the throughput, get your answers, and then slowly use another cluster to pump it out somewhere.
Okay.
So writing it locally, I think, will help.
Okay, thank you.
I hope so.
Hi, thank you very much. So I have 2 questions. So one is, when I was listening about persistence and caching, it seemed very much that this is a pretty simple decision tree in terms of that you just decide if you're writing to few places afterwards, then you need to cache, otherwise you should not because you will take too much memory. So do you think this can be somehow automated inside of Spark, or there are more to it and logic is actually more complicated?
You're talking about like in the Spark, can Spark reverse analyze the DAG and see if there's redundancies?
Exactly, yeah.
It's a fair question. I encourage you to help us write that. Perhaps.
That's right, yeah.
It's a good idea. I don't know.
I'll create an issue.
I think it goes to the heterogeneity of all the jobs though. But yeah, it's a good idea. Get it, why don't you go ahead and write it and we'll get it in Spark 3.0.
And the other one, so you can imagine that everybody is struggling with this. I've been working with Spark for like 5 years, I think, and it's not getting easier. So do you think, I asked you already in San Francisco if you're going to create some kind of a book or a cheat sheet on this. So do you think it's still, there is a plan to do this?
All right, so the question there was about a book that I leaked that I'm writing. Last time I did this talk, and yes, it hasn't changed much since then. But there was some delays on getting it published. So it's still in the works, and I still fully expect. Basically, this book is a deep dive of what we talked about today. That's even deeper than what we went today, with examples and screenshots. Yes, I want to get it out, and yes, I'm still planning to, and I'm planning to release it for free as soon as I can.
Great, thank you.
Hello.
Hi.
2 short questions. How fast is Java underscore method from built-in SQL functions, which uses reflection? And second is, how fast are Scala UDFs imported to Python using Spark register Java function?
Okay, I think the first question was how fast is Java functions?
No. First question was Java underscore method.
Okay.
When you use expression, Java underscore method, and something from Java.
I believe that would still be deserialized. The way that you could answer, so you have basically 2 different speeds. You have the vectorized functions and the non-vectorized functions. If it's vectorized, you'll see a whole stage code gen, which means you're actually getting down into bytecode, so you don't have to go into all of the Java objects. So if you get into Java objects at any point in time, you're on the slow side. I can't tell you exactly the speeds. I think there's actually some good papers in our blogs that have been written about the speeds between them. But I can't, I mean, I put them into two categories. There's slow and there's fast. Slow is whenever you don't have a whole stage code gen, and you'll see the different stages there. Sorry, did that help at all?
Okay, and when you import your Java UDFs using register Java function, does it work fast?
I can't say I can answer that because I haven't used Java in a very long time on Spark.
No, it could be written in Scala.
So if you're talking about the standard SQL register UDF, if you register a UDF and that UDF is taking in primitives, it'll be the non-vectorized kind.
No, I'm talking about Scala function which compile into jar, and you pass this jar as a class path, and then in Python you call Spark register Java function and then use it in expression.
Yeah, I believe that still is going to go down to Java objects, and so you're still going to be on the slow side, I think. I believe that, and you can tell in the SQL plan for sure by looking at that, and if you don't get a whole stage code gen, then it will be on the slow side. But I believe that when you call those, because you're working with primitive types, you're working with Java types, not column types, you're going to get out of the vectorize. Unless you write your own vectorization functions, which you'll have to go into the SQL functions and look how they vectorize it to do that.
Thank you.
Yeah.
Hi. Sometimes you have to do a join of two data frames, but not just on a single column, but on, for example, multiple columns. And they just say join on this column or on this column. And I noticed that it does actually this cross join. So I ended up with 10,000 of tasks. So what I did is then do each join separately and then a union. Do you have any better ideas how to do it?
Yeah, that's always been a tough one. There are some fancy, I use in Python or Scala?
Python.
So yeah, in Python there's actually, I've seen a client write it where you can actually do a pandas UDF and use the apply method for a grouped UDF on the right side, on the small side of the join if there is one. And on the small side of the join you can get clever with how you can look at that and do introspection on which way to do the join on the right hand side.
Okay.
It's a little tricky, but I saw it worked. I was pretty impressed. But yes, there is a way to get out of those cross joins in most cases. I think there are definitely going to be edge cases to that.
Okay, cool. Thank you.
Thanks.
Hey, thank you for the talk. Simple question. So as a rule of thumb, we usually, after reading in the input files, we just shuffle partitions based on the number of partitions in the input files. Is that a bad idea? I mean, usually that number is higher than the number of cores we have. So
You're talking about the read partitions?
So we read in input data, which is usually from Parquet, comes in like 128 megabyte blocks.
Right, exactly.
We take the count of that, and then we actually say, well, this is going to be the number of shuffle partitions we want to
Yeah,
have.
that doesn't work. The reason that doesn't work is because usually you're going to join more than one data frame. So if you sum up, let's say you take 3 of them, and you have data frame 1, 2, and 3, you're going to join all of those, or group by one, and then join by some later.
Yeah.
What happens is those first 3, yes, initially you can sum those up, but then it's not going to necessarily be your biggest shuffle stage. Also, the sum of those, they're not guaranteed to be bin packed always to 128, but that is the best way that I found to try and build those validation functions, is to look at the input partition counts that I have to begin with. But you have to keep in mind the types of generative, if you're generating data, what your Cartesian products are, because that's for the thing, right? Your Cartesian products are going to be much bigger than the input data. Not to mention, they're going to be compressed and serialized differently. So maybe if you try to take your input size and take some factor, like some coefficient, maybe 4 or 8, whatever you find for that workload, that might be a good way. But usually just taking the number of your input data frames and summing them up doesn't usually work. It's a good starting point, but the right way I think is to take the data frame, take the workload, do it with a subset of data, like 10% of your data, run through that, and then know that, find that equation that works right, and then know that about 10 times that is going to be your production size. And then maybe add a few hundred or something partitions for safety.
Okay. Next question. I have 2 more. Regarding the repartition before writing out, so the coalesce gets pushed up, and that's really annoying. So in the end,
Yes.
we ended up using repartition. So you're arguing that you should do the barrier to kind of write out the data and then kind of read it back into
The repartition, yeah. That,
so the question I have is, writing the data out might be more costly than just doing a shuffle.
if you write it out to a remote storage, possibly. But if you can write it out to local disk somewhere with a local checkpoint or using auto-optimize, that is absolutely going to be faster.
Then a shuffle.
Then a shuffle, yes.
Okay.
If I say absolutely with caution, so probably let me say that. But I would test it, but I don't like to do the extra shuffle stage because I think the write and read with the coalesce is going to be faster. But test it. I usually find that the write, the read, and the coalesce is faster.
Okay. I haven't written down my third question, which I've now forgotten. So.
Well, come back if you remember.
Hi, so in the RDD API, you can manually specify the partitioner. And this could be useful when, for example, both RDDs already have the same partitioner and you want to join them. Then you can avoid an extra shuffle stage. So can you give us an insight how this partitioner management works in the dataset API? When you lose it, when you actually retain it, etc.
And are you just specifically talking about dataset or data frame dataset, or does it matter?
You can explain both, I guess.
Okay. So the questions regarding custom partitioners. So if you have some kind of data set that's kind of custom, or that you can, like protobuf or something that's a little bit strange and you're trying to join stuff on that, on geospatial data, something like that, absolutely a custom partitioner is going to help you avoid skew. So typically when I write a custom partitioner is to avoid skew or hotboxing or something like that. And yeah, you can absolutely find clever methods to avoid shuffles. I haven't, the same is true for bucketing. If you can find something specific enough for the bucket, you can actually avoid the shuffle by using bucketing. But there's avoiding all shuffles with custom partitioners I haven't been very successful with, and that maybe I'm just not capable. But it's pretty challenging, although custom partitions will definitely help you avoid the skew and definitely help you optimize your jobs. Whether or not you can fully get rid of the shuffle is questionable, because it's challenging to make sure that you have the right number of cores, because we have these clusters that change size all the time. So making sure that everything gets put to the right place to make sure that during the join they're on the same core. It's a very challenging thing to do. I'm not saying it can't be done, I just think it's challenging.
Okay, and another quick question. How do you think we should compute the number of partitions for queries which could have input sizes from 200 megabytes to 200 gigabytes?
Partitions that have different sizes?
I mean, like input sizes. Like if we have input sizes of 200 megabytes and 200 gigabytes, how should we set up the number of partitions so that it works well for both cases?
So you're talking about workloads that do that have shuffle stages where
that can significantly differ in the input size.
Good question. Do the biggest one. You have to size the shuffle because you can only do it per action. So my jobs are always changing that between my actions. And if you can't change it between your actions well enough, maybe you can break apart your action into 2 actions or something to get some of those stages out that are much smaller. If you can't, then you have to size it for the biggest stage, the biggest shuffle stage in that action. But after that action is done, then you can change it again. So you can move it between actions, but for that action, the biggest stage is the one you have to go for. Another one you can do is actually minimize the stage, minimize the shuffle stage by trying to do more lazy loading or getting rid of some of that data, throwing it out, doing a function to get rid of something like that.
So just a generic point, I know that the shuffle partitions is kind of a global config value, but it seems to me from the API perspective, it would have been more useful if it was on the operation that would cause the shuffle. For example, if you're doing a join, the join is going to do a shuffle, and then you kind of hint to the join how many shuffle partitions you want to end up with. And now kind of it's a global parameter which you have to kind of set in awkward places in your applications, which makes it a bit weird.
Yeah, you just have to set, I mean, it's kind of natural second language at this point for me to just set the shuffle partitions before the action based on, because I never work with the full data set to start with. On big data, I always subset the data. And so as I scale up, I know what those numbers should be. So I just kind of write them. Yeah, maybe that would be a good idea. I haven't done it.
Okay, now remember my question. So it's to do with data locality. So if you have two data sets, which are, let's say you have, your stock adjustments, which is some kind of temporal time series, and you have your orders, which is purchases in a shop. And then you know that there's a common partition key for both of these data sets. So under ideal conditions, when you load these two data sets, you would like both sides of the data set for the same partition key to end up on the same node.
That's kind of what he was talking about with a custom partitioner to try and force the data to the same place.
Right, so you could do that on reads, not only for writes. Because I was under the assumption that a custom partitioner only matters when you write data out, not when you read it in.
Well, you have to have the shuffle. So a custom partitioner, when you read the data, you can specify the partitioner to use. And if you specify the partitioner that's going to be used, and maybe you have to do it on a repartition, actually I take it back, you're right, I think. Now I'm going in circles. No, there is a partitioner that does the read. There is a way to change the partitioner on the read, because that's going to tell you. But you have to change the data source. That's what it is. You have to create a custom data source.
Yes.
And a custom data partitioner. So if you have the two of them that share the same logic on how you're going to put the data on the RDD, where you're going to put it, then you could force data locality to some extent.
Okay, but it does require essentially a custom data source.
Yeah, it is a custom data source.
Okay.
Hello. Is this code is trying to optimize the driver overhead in the final commit with the fork join?
This is optimizing all the nodes, all the cores, because it's going to use the driver a lot because it's going to have to schedule a lot more, but it will actually force more data and it's going to shove more tasks, stack them, so that the executors, the slots, remember if I have 2,000 slots available and this one task is hanging, well, while that one task is hanging, 1,999 tasks can still be being operated on elsewhere because they're independent of this one. So all the executors are going to be used, and that's how I'm going to get to 125% and maintain that for a certain period of time.
Can I not get that by 500 into parallelism that you have written there?
Well, you can, but if you have a partition that kind of hangs, then it's not going to be able to. You're going to be waiting for that one to finish before you start the next one. This will actually break that apart and let you do multiples at one time, multiple stages at once. So you'll have a bunch of pending stages and a bunch of stages executing at one time.
Okay, got it.
All right, Daniel, thank you so much for all your time today as part of our tutorial. I'm sure Daniel will be sticking around for any additional questions that you may have.
Thanks, guys.